So good afternoon, ladies and gentlemen. My name is Shuzhe Zhang. I'm currently working as a PhD researcher in Delft University of Technology. Today, I'd like to talk about the development of a strain-hardening geopolymer composite through micromechanical modeling. I'd like to take the chance to thank my supervisor, Dr. Guang Yi, and also Professor Victor Li for holding me in University of Michigan during my research visit. So the strain-hardening cementitious composite SHCC offer extraordinarily tensile strain capacity, as shown in the figure on the left. It has almost several hundred times higher strain capacity than conventional concrete. The matrix of SHCC also is reinforced with shortcut fibers, which enable it to have the multiple cracking property, which is also beneficial since it leads to tiny cracks with very small crack width at the surface instead of one single crack into the surface, which is beneficial for the durability. However, SHCC has its own problems because preparation of SHCC needs high amount of cement, which could largely compromise its sustainability. Researchers have already applied SAMs into the SHCC to increase its graininess. However, there's still much room left for us to improve. Geopolymer as alternative binder, on the other hand, is environmental friendly and sustainable. It also have comparable and better performance and durability than OPC binders. So it makes us wonder that what if we substitute the cementitious matrix in the SHCC by the geopolymer ones? So why not we're making strain hardening geopolymer composite? Why not SHGC? However, we do have to note the challenge here that SHGC development is still a multiple factor optimization problem. So traditional trial and error method is still not suitable for development of SHGC. So the aim of this research is to develop SHGC using micromechanical modeling as able guidance to save us from the trial and error process. And also another purpose is to evaluate the visibility and effectiveness of using micromechanics as design basis of SHGC. So before we go deep into the presentation, I would like to make a very brief introduction on the mechanism for strain hardening behavior to happen. So the most important thing for the strain hardening behavior is that a steady state cracking of the composite under tension. So otherwise, you will have a Griffiths type crack, and which finally leads to strain softening behavior of your mixture. And this is what normally happens with conventional concrete and also conventional fiber reinforced concrete. To further assess this steady state cracking, we have to check the single crack plane and its behavior, which could be characterized by the sigma delta relationship, or in other words, fiber bridging stress versus crack opening width relationship. So as shown here in this figure, and also in the equation, it shows that the total work onto the crack body is consumed partly by here. This part is the crack bridging as the strain energy, and also another part is consumed by the crack tip opening during the crack propagation, which corresponds to here the J tip. Another very important term is the complementary energy, which corresponds to the left part of this equation, and also the maximum complementary energy is actually calculated using the crack bridging in the sigma delta curve. So to ensure the energy balance, we have two criteria. The first one is the strength criteria, which controls the crack initiation. And the second one is the energy criteria, which controls the crack propagation. So when both of the criteria are met, we can have a steady state cracking, and finally we'll have a strain hardening behavior of the composite. So to further quantify the two criteria, we introduce the so-called pseudo strain hardening index, PSH index. We have the first one, the strength PSH index, PSHS, equals to the fiber bridging strength over the first cracking strength of the matrix. And also we have the energy PSH index, which is PSHE equals to maximum complementary energy over G tip of the matrix. So theoretically, the values for both of the indices should be higher than 1. However, as reported by researchers, they found that in the experiment, a PSHS value of 1.5 and a PSHE value of 3.0 is more beneficial for a robust strain hardening behavior to happen. So for the calculation of the PSH indices, we use the matrix property determined from the experiment. This is the first cracking strength of the matrix, and this is the J-tip of the matrix. And also we used output from the micromechanical modeling. This on the right-hand side is here, which is the fiber bridging strength and also the maximum complementary energy. And also a very brief introduction of the micromechanical model we're using. We're using the micromechanical parameters to build up the single fiber pull-out behavior, which depicts one fiber bridging one single crack. And then we use the fiber distribution function at the crack plane. We try to scale up to the composite behavior and come up with the sigma delta relationship as the output. So from this sigma delta relationship, we can calculate the maximum complementary energy and the crack bridging stress. And these values could be further used for calculation of PSHS to evaluate the strain hardening potential of the mixture. So the starting point of our of this study is a geopolymer matrix we developed before with very good mechanical properties and workability. So we use slag and flash for the matrix and sodium hydroxide and sodium silicate solution as alkali activator. We actually fix all the parameters except for the silicon modulus, because we found that matrix and the interface properties are quite sensitive to the silicon modulus. And we cure our sample in climate chamber 20 days before testing, and the PV fiber was used for the composite and also single fiber pull-out tests. The matrix properties are tested using various experiments. This includes the elastic modulus, compressive strength, and we tested splitting tensile strength as the first cracking strength of the matrix. We also determined the fracture toughness, K1C, and combined with the elastic modulus, we can calculate the crack tip toughness, G-tip, which will be further used for the PSH indices. So the matrix properties are shown here. And also we determine the interface properties using single fiber pull-out test as shown here. We are using a precision cut-off machine to cut the fibers and the specimen into very thin slice. And we are using micro compression tension device to pull out the fiber as shown in the video. So here shows the results from the single fiber pull-out test. And from these results, we can calculate 3 very important interface inputs, which are the chemical bonding energy, GD, initial frictional bond, tau 0, and also the slip hardening coefficient, beta. So the results are further shown here in box chart. As you can see here, the interface properties shows a relative higher standard deviation in comparison to mechanical properties. However, this is quite reasonable since the fiber surface, the heterogeneous coverage of the reaction product on the fiber surface is actually inevitable at this scale. So we also identify the consistency between the GD and the beta, which both of the factors are more chemically related to the reaction product. And also the frictional bond is more physically related to the fracture surface roughness, and also has some influence from the shrinkage reduced stress onto the fiber surface. And as the first step, we're using the micromechanical modeling to aid the selection of suitable fiber volume and fiber length. So what we do here is that we use, we set the energy and the strength requirements, which is PSHE equal to 3 and PSHS equal to 1.5, which are normally used for SHCC materials. So we try to incorporate all the matrix properties and the interface property tested from the experiments into the model, and we only try to change the fiber volume and fiber length to meet the two requirements. This is done by inversely fitting, and all the results are shown on the left. As you can see here, all of the curves, both the black one and the red one, the points on the curve are the critical values to meet both requirements. And the area above both curves is actually the one suitable for selection, which meet both PSH requirements. And since we want to choose the fiber volume as low as possible, since to reduce the cost and to avoid further mixing problem in the future, so finally we choose the fiber volume at 2% and also fiber length of 8 millimeter for all matrices. So afterwards, we try to incorporate these two values along with the interface and the matrix properties, and we use micromechanical modeling to calculate the sigma delta relationship. You can already see that for all of the mixtures, it already have very intrinsic differences among them, which means they should have different strain hardening behavior. And we also try to calculate both PSH indices for all mixtures. As you can see here, all mixtures at least meet minimal requirement for two PSH indices. However, it seems that the PSH strength plays a more dominant role, since, as you can see here, apparently the PSH energy has a larger margin than the PSH strength. And finally, from the modeling, we can already see that the mixture M1.2 should have the best strain hardening behavior, because both of the PSH are very high. And finally, we try to use uniaxial tensile test to evaluate the tensile performance predicted by the micromechanical modeling. And all the results are shown in here. And it is found that the simulated PSHS, especially the simulated PSH, especially the strength PSH, is in very good agreement with the tensile strain capacity. And more importantly, as predicted, the mixture 1.2 yields the best performance. And with this, we also try to conduct the DSE analysis on the multiple cracking behavior, and this shows that this mixture almost shows saturated multiple cracking. So with the tensile strength capacity of 4.8% and ultimate tensile strength of 3.8 megapascal, this SGC mixture seems very promising and is also comparable to conventional SHCC with moderate strength. So finally, come to the conclusion. I will not go in deep, but the most important thing is that this study demonstrates that the micromechanical modeling is a very effective tool for development of SGC. It can help us assist the selection of suitable fiber properties while predict the potential tensile performance. So finally, I would like to recommend one of our research publications earlier this year on CCC. So most of the information in this study are inside if you are interested. So I would like to stop here and thank you all very much for your attention.